Good morning. Here we are yet again for another lovely session of CENG 3325 Structural Analysis. Today we're going to pick up where we left off in the and we're going to move on to covering some basic elements of support, determinacy, stability, and other related topics. So the first thing I want to look at today is support conditions for 2D trusses and frames. So support conditions for 2D trusses and frames. So this is definitely going to be a review from statics, but it would be good to have it in our videos and lectures here. Support conditions for 2D trusses and frames. So I'm going to describe these for two-dimensional systems, and then I'm going to also illustrate how these would work in three-dimensional cases. But with most of the frames we deal with in a class like this, they're going to be 2D. For 2D trusses and frames. Support conditions for 2D trusses and frames. So we have three main ones we need to consider. This is going to be our famous roller, pin, and fixed supports. So we have roller, pin, and fixed. Again, just a review from statics. More roller support. Pin support and fixed support. And fixed support. And for each, I'll draw out two variations you may have, but I'll first define them. So a roller, of course, is able to resist resist translational force in one direction. So resists motion in just one translational direction. In one translational direction. A pin support, of course, resists motion in two translational directions. And a fixed support resists motion, resists translation in two and moment in one, or rotation in one, I should say, if I'm going to be consistent with translation. Resists translation in two directions and also rotation. And resists rotation. So, and as far as what these look like, this roller support is always defined as basically the translational force is always defined perpendicular to the surface. So we could draw something like this where we would have a roller support, simply like this. Or we could even have a variant that might be up against a wall or something. We might have a wall like this, and we could have a roller support like this, something like this here with a frame coming out of that there. And then let's show the forces that would be resisted by this. I would have one translational force perpendicular to the surface. And this translational force can be either horizontal or vertical. The important thing for a roller support is that the force is perpendicular to whatever surface the roller support is on. Next, let's consider pin supports. And these have many variants, and all of these have many variants, including another variant of this would be something like the rocker support, and et cetera, et cetera. There's many different versions of this, but the pin support, we could also have this on either a horizontal surface or on a vertical surface. Typically just drawn as a simple triangle, something like this. Again, this should all be old hat to you by now after statics and mechanics of materials. This is just a brief review. And we could have something like this. Maybe more like this here. A pin support here against a wall. And let's show the forces on here as well. Here I would have a horizontal force, and a vertical force, and a horizontal force, and a vertical force. And finally, we can have our fixed supports, which will be simply a, when you're drawing a frame diagram, will just look like a line going into a surface. So something like this. If I can manage to draw a straight line. Something like this. Or something like this. And then let's show the forces or the reactions here. We will have reactions, our X force, or our X reaction, a Y reaction, and a moment. Same here, X reaction, Y reaction, and a moment. And that is the fundamental difference between pinned, fixed, and roller supports. Now, these definitely come in in all sorts of configurations and such, but I think I also might mention how these are represented in the real world. So what do these things actually look like? So this is how they look when we draw line diagrams and simple models and things like that. But what does a pin support, a fixed support, a roller support, etc. look like? So real world examples. Now some photos would be nice here, but I can do some simple drawings here for now. Examples of supports. Supports or connections. So let me show you maybe if you have a roller support, usually that's something like just one object bearing against another. Usually one object bearing against another. And bearing, of course, means two large objects, two surfaces in direct contact. So, for example, if you have a bridge pier, so you have a bridge pier here, maybe a beam here and a column here, and then you have your major girders here, and then imagine you just have your major bridge girder just sort of sitting on top of this thing. Or alternately, you might have this on a set of embankments, if it's just like a single span small bridge, highway bridge, that sort of thing, overpass. So if your bridge is just sitting, if your actual major girders are just sitting like this, and this is done frequently, where you'll have, this is done frequently where the ends of the beam will just be laying right on top of the piers here. Well, think about this. What kind of forces are going to develop on the ends of this? What kind of reaction forces are going to develop on the ends of this? Now, truth be told, there would be some lateral force, X and Y, from what? What would that force be from? What would the XY force be from? What would the XY resistance force be from on this bridge, on this girder here? Friction, exactly. Concrete and steel tend to weigh quite a bit. You know, they're if you're not familiar with that, you may be in the wrong major. But steel and concrete tend to be quite heavy materials, and just like anything else, if you put one heavy thing against another heavy thing, and you have concrete tends to have fairly rough surfaces, so not the best coefficient of friction. So that, yes, that does develop substantial frictional force. However, when we talk about pin and roller supports, we're always talking about really something in proportion. So yes, frictional force, lateral frictional force does exist in here, but compared to the actual strength of the member, like if you measure the say the tension force, like the force that would be required to fail this girder in tension, and compare that to that frictional force, the frictional capacity of that joint, that's going to be minuscule compared to the tensile capacity of the beam. The beam's going to have, 10 or 50 times the. If I try to pull on this beam, in other words, if I have a crane and I pull on this beam really hard to the right, the beam is not going to cleave in two. Rather, what's going to happen, it's going to slide off the abutment over here, or the pier over here. So when we talk about, this really brings us to the idea of engineering models again, like you hear in many courses in statics and mechanics, materials, etc. A pin and a roller support fundamentally are engineering models. They are approximations to real-world conditions. So what about something like a pin support? What does a pin support look like? So for example, let me give you an example of, say, a steel connection. if you remember from mechanics of materials, if you remember back from your mechanics of materials class, at least if you had me for mechanics of materials, or some other competent instructor, in other words, not me, but because I'm obviously not competent. So anyway, think of a W section. How does a W section work mechanically in terms of bending? What is the basic logic behind a W section? What's the basic logic? Why is it designed the way it is? Should hopefully remember this from mechanics of materials. Exactly. It's the whole idea of a W section is to maximize moment of inertia. You're trying to get as much of your cross-sectional area as far from your centroid as possible. So now what we do in steel design is we basically say, we assume that the flanges here and here carry all of the moment and the web carries all of the shear. That's not a perfect approximation, but it is good enough for most design cases. So we treat the flanges as carrying all the moment and the web as carrying all of the shear. So in turn, if you want to create a pin connection between on a W section, if you have let's say you have a beam coming into a column, and you want to join a beam to this column. This is a column. This is going to be the beam. If you want to connect these two, what you do is and if you want to connect them in a pin connection that will only transfer vertical and horizontal force but not moment, you only connect up the web. So you use something like a shear tab or something like that. Maybe you weld up here, maybe do a fillet weld here, and then do a couple bolts here, or you could weld there as well. Just a very simple connection that connects only to the web, and by not connecting the flanges, your connection will not have any moment capacity. It will only have will only have translational capacity. This is what a pin connection typically looks like in the real world, something like this. And when doing concrete design, you do something similar. You connect up your, you basically don't connect up your major bending reinforcement. You do connect up shear reinforcement, things like that, etc. And then a fixed support, at least for a connection, is going to look very similar for steel anyway, but we're going to add something that will also connect up the flanges. Now, truth be told, does this connection have zero moment capacity? No, of course not. I mean, if I think about this, I have a bolt here and a bolt here. Even if this bolt is right, imagine this bolt is right at the centroid. If I try to apply a moment to this, I have two bolts separated by a certain moment arm. Every time I have forces separated by a distance, I have moment capacity. Now, but again, we got to come back to all of this is defined relatively, or all this is defined relatively. So the moment capacity of this joint, this little shear tab here, compared to the moment capacity of this large beam is minuscule. It's probably less than 10% of the moment capacity of the entire beam. So again, just like roller supports, pin supports are defined relatively. They are engineering models. We're going to assume that they have zero moment capacity, but in truth, they do have some non-zero moment capacity. But in most cases, not in all cases, but I should say in most cases, you can almost always in engineering get away with assuming less capacity than you have. So if I assume that I have less strength of the joint than I really do, that's what I'm with all these assumptions. When we assume a pin, when we actually have some moment capacity, in most cases, in almost all cases, that's a conservative assumption. In reality, I would have some resistance at that joint, but I'm neglecting it and saying, you know what, let's just assume that's a pin support for analysis sake. But it's a conservative assumption because I'm basically just saying that little bit of extra capacity there, it's actually going to help me, but I'm going to ignore it for the sake of engineering analysis. But that's not always the case. There may be some cases, some edge cases, detailed finite element models, or maybe some more complex seismic analyses or something like that, where that might actually break down, where that might not be as conservative assumption as you would think. But in most general civil engineering cases, it's going to be a conservative to assume a pin where you'd otherwise have a fixed. Although the one case you have to be careful with, I guess probably the major case, is where you have maybe a continuous beam. If you had a continuous beam going across multiple spans, if you assumed those were simply supported and assumed they were just pin, pin, pin to be lazy and make analysis easy, that would actually that could potentially cause a large problem, because with continuous spans, as we'll see later in the semester, you can actually very easily get negative bending moment. And if your beam does not have identical positive and negative bending moment capacity, especially like concrete beams, that can cause a big issue. Like if you have a big beam that goes between multiple spans, if you just assume that's, oh, just a pin support, pin support, pin support, that is actually not a conservative assumption for the case of negative bending moment, but maybe that doesn't make a lot of sense right now, but we'll get to that in a bit. So let's show this as let's show first the web connected up, and this is totally not to scale. This is awful. So maybe this is connected with another weld here. Maybe this is let's make things interesting. I'll make this a bolted clip angle, and this would be connected here, maybe with some bolts. And then I would need something up here, some flange plates to mobilize the flanges and give me some sort of moment capacity as well. Not to scale, not to scale, not to scale. So maybe have a fillet weld here, maybe some sort of fillet weld here or something, maybe up here. But anyway, the whole idea is that I'm just going to be doing something to connect up the flanges in addition to the web. Okay. And I also want to discuss pin versus rigid joints that appear inside frames. So you most likely, or hopefully, well, actually, probably if you took statics and you remember statics, doubtlessly you remember pin, fixed, and roller supports. But you may not have seen before pin joints, fixed joints, etc. Now you could have a roller joint, but I don't really deal with that. We don't really deal with that much in frames. So I'm going to focus mainly on pin and roller joints, or sorry, pin and fixed joints in frames here. So let's look at joints, pin versus fixed, or pin versus fixed. Joints, pin versus fixed. Pin, and you could call them pin, you could call them pinned, what have you. Versus fixed. So pin joints are going to be joints like actually I drew here. So I drew previously. So I should probably go back and say, technically what I drew there is probably not actually supports. Those are more joints. But it is a great way to illustrate the mechanical real-world differences between pin versus fixed. If I wanted to have a pin support on say a column coming into the ground, instead of that thing, instead of the column joining, instead of showing a beam and a column, that would basically just be coming into a foundation pier or something like that. That's what a pin support would really look like, say on a building column. But on a pin joint, let's look here. Pin joints. Again, here, let's see. They're going to carry only axial force or shear at the joint. Will carry only axial force and or shear at the joint. So I want to relate this back, not just to X and Y reactions, but to the internal forces that we've seen previously. So a pin joint will carry only axial or shear force at the joint. In steel members, in steel sections, formed by connecting only the web. So I might draw a frame. Let me draw a frame, and I'm going to draw it both sort of as a combined view and then as an exploded view. So I could have something like this, and this here. So imagine I have maybe one end of this fixed here. Oh, then I could have another end of this fixed here. And then maybe a pin here. Now, if I explode this and say, okay, what kind of forces will be transferred through that joint? Let's take a look. So let's look at this force here and this force here. or this member and this member. And maybe I could call this, I don't know, fx here, and fy. And when we get to do doing more thorough analysis of frames, we'll have to develop a more, maybe a more systematic way of naming these things, a systematic number and naming scheme, lettering scheme. But for now, this is going to be fine. So a few things of note. When assuming directions on internal forces, you can assume whatever direction you want. So, if I were doing an analysis and actually trying to find the forces here, internal forces, etc., if I assume this is to the right and this is to the left, that's fine. Or I can assume this is to the left and this is to the right. The one thing I really have to be careful that I do in internal forces is what, though? Equal and opposite, yes. So we still believe in the laws of Newton. As long as we still believe the laws of Newton, as long as we still fear Newton's ghost, we still need to obey the laws of Newton. And so for every action, there is, of course, always going to be an equal and opposite reaction. So if there is an Fx force to the right on this member at this joint, then there must be one to the left on this member here. And also, that's one thing to note. Another thing to note is that one member's axial force can become another member's shear. Can become another's shear in certain cases. So think about that. Think about the end shear, actually. Well, it'd be the end shear, and then it would end up being basically an end force there. So that would be the starting point of the shear diagram. But for example, this Fy, this is for the column here, that is an axial force. But when it enters the beam here on the left end, that is going to be the starting value of the shear diagram. So, and certain supports, when things like axial force and shear, these are internal forces. They are not global forces. They are local forces. They are forces defined in relation to a member's local coordinate system. Or usually we define like the x-axis along the length of a member, something like that. And so local forces can, when they go between members, an axial force can become a shear can become an axial force. And, that seems, and hopefully that's fairly intuitive. Okay, so next I want to look at fixed or rigid joints. And look at the internal forces therein. AKA moment connections, what we refer to as moment connections. So, of course here, as we discussed already, I just want to put it in this form, all three internal forces will pass through the joint. Will pass through the joint. And then here, but also important to note that if not otherwise noted in frame diagrams, connections are always assumed fixed. And let me draw out what that means. So, for example, if I have a frame here, in a simple frame diagram, this is just represented by 3 lines coming into our 2 joints. Notice there's nothing indicated here. There's no pin or roller or any kind of circular thing. Do be aware, usually when you have a circle like this in a joint, this refers to a pin joint rather than a roller joint. And the reason for this is if this were only a roller joint, that really wouldn't make sense for an internal joint. Like, how would you have just force in one direction at a joint? Why would anyone build something like that? That really doesn't make much sense. Your frame would basically be collapsed at that point. So it's very, if I tried to build a roller joint here, this beam would, well, I guess it would just be a cantilever at that point, or this would be a cantilever, either or. But notice a circle in a frame diagram will indicate that that joint is a pin joint. But if you just have lines coming into a joint, that is indicating a fully fixed connection. And then if I show the internal forces here, and I suppose I could give these some names. Let's say this is joint A and this is joint B. So I'll name the forces accordingly. And I will label them, being very careful to keep everything lined up properly. I guess I could label this C and D, although we're not really going to need that. Oh. There. There would, of course, be 3 potential reaction forces here and here, but I'm only labeling the internal forces for this. So I would have some sort of AX, AY, AY, and then an MA and an MA. And again, we're taking notes that all of these need to be in opposition. If the moment at A is going clockwise, if the moment on this end is going clockwise or is going clockwise, let's say, this one would need to be counterclockwise. If this one is counterclockwise, this one needs to be clockwise. Again, we need to make sure we can assume whatever direction we want. We just have to be internally consistent. Let's see. So then we would have BX and BX, BY and BY, and then some sort of MB and MB. Any questions on this kind of member internal forces definition items? Okay. All right. So next I want to look at determinacy and stability. Determinacy and stability. And this is discussed in the Hilbert text, but I thought I would go into it here. First, I suppose it would be good to define determinacy and stability. What do we mean by each of these? Let's define these first, then discuss some basic tools on how to determine each of these. How to determine determinacy. So when I say determinacy, what do you think I mean? What kind of determinacy am I looking at? When I say there's sort of a missing word there. Determinant. When I say determinant, I mean, do I mean that it's just a very difficult problem? Is that what I mean? Is if something's just really hard? Is it determinate? Is it indeterminate if it's a really difficult problem to solve? Statically determinate. Yes, statically determinate. The determinacy ultimately comes down to statically determinate. So I remember I once had a statics class, and I had some fun on the sort of. I had some multiple choice questions at the start that were going over some basic theory, and I gave some definitions for static determinacy, and you had to select the right one. And I had some fun with like answer D or something, and it was something like, a problem is so so incomprehensible, it is utterly inconceivable and unsolvable by mere mortals alone. And I think one person actually did circle that. I guess they just were not feeling so well on that exam. So, utterly unsolvable by mere mortals alone. That is not what determinacy means. Determinacy means a frame is determinate I guess I could say a frame or structure is determinate if all reactions and internal forces can be found by applying the laws of statics alone. So everything you learned in statics class. So some examples of this would be things like, nice simply supported beams would be a very statically determinate system. You can solve for all of the internal forces just by using the method of sections. You can also use trusses. Simply supported trusses would be a great example, etc. In fact, I want to give some more notes on this, so I think I'll come back to that. And in turn, when I talk about the laws of statics, there are certain things in relation to this. So what do we need to solve a problem statically, though? To solve a problem statically, we only need the frame geometry, nothing more. We require only the frame geometry. Geometry and support conditions. Geometry and joint/support conditions. In other words, when you're talking, when you were learning statics, when you were solving for a shear and bending moment diagram, were you ever asked to, were you ever told that not only solve for the internal shear and bending moment diagram at a point in this beam, and oh, by the way, the beam is a W so and so by so and so, or it's a concrete beam 8 inches wide and 12 inches tall? Were you ever told that? No. Why not? You don't need it. Exactly. You do not need it. And so if you have a system that is statically determinate, you do not need to know anything about either the material properties or the cross-section. That's the nice thing about statically determinate systems. The nice thing about them is that they have, that you only need to know the geometry of the frame itself, basically the frame diagram. Again, these are very, determinate systems are very easy to solve. Systems are very easy to solve. Now, there is kind of one hidden downside to a lot of statically determinate systems, though, statically determinate designs. Any of y'all aware of that? The reason fundamentally that static determinacy works, well, that you can just look at a frame and say, based on the applied loads and geometry, based on just that, where all the loads are and what the internal forces are, things like that. In determinate systems, there is only one place for the load to go. There's only one way the load can go. Maybe I can draw that on the next slide. Again, there's only one way the load can go. Okay, so we'll see what that means over here. So again, we have, because what allows us fundamentally to solve for all of these internal forces in our members is that based on the geometry, we're actually restricted to only one single possible set of load paths. So in other words, if I have a truss, say I have a truss, something like, oh, that's really, oh, there goes my truss. say I have a truss with, there'll be a top chord and a bottom chord. There'll be tension members, compression members. Basically, let's say it's a nice basic, simply supported truss. Load at the middle, something like that. And a downward load, so the top chord will be in compression and the bottom chord in tension. So I apply a load like this, top chord will go into compression, bottom chord will go into tension. There is only one possible way that loads can be distributed in this truss. In other words, assuming these, of course, are all pin joints, for it to be a true truss, they would have to. And so, again, in other words, this top member has to be in compression. This bottom member has to be in tension. If I said this was, I don't know, 10 kips or something, and I knew that if I gave you the geometry, we could solve for all of this and say, this has to be this. Or in other words, I don't have any choice in what force this member has to carry. If my math shows that this member here must be able to take 20 kips of load, it has to take 20 kips of load. There are no alternate load paths available. In other words, but compare that to something like a fixed frame. If I have a great big frame with lots of different load paths, like fixed everything, yes, it's more difficult to analyze, but structures like this have many load paths. And that's what makes them difficult to analyze. The same thing, though, that makes them difficult to analyze gives them structural redundancy. So say I have a structure like this. Something like this. 3 columns in one frame line here. I have 3 columns, a whole bunch of fixed connections, fixed supports, etc. If I start applying a load, imagine I start applying a large load here. Let's say this center column starts to get a bit overloaded. Well, it's not going to immediately cause global failure of the structure, because what might happen is if there is enough stiffness in here and in this column here, if this one can't take the required load, it is possible that this guy over here and this beam over here may be able to distribute that load to other structural elements. Again, in statically indeterminate systems fundamentally represent redundancy. Statically indeterminate, and often this can lead to efficiency, especially in the case of like a good example of this would be continuous spans, beams that span between multiple, say you have a very long highway bridge beam that goes between multiple supports. That is an example of an more indeterminate type system that produces higher efficiency generally. So, but statically indeterminate systems, typically, there may be some exceptions, typically have greater redundancy.
You said the top of a truss has to be in tension and the bottom has to be in compression?
Vice versa. The top will be in compression, the bottom will be in tension. Typically, under typical conditions. Now, there are a lot of caveats to that, like if I moved this roller here, so there was a cantilever, part of the truss was like cantilevered or something, in that case, it would be very easy to end up with negative bending moment. Or if for some reason the truss was supporting like an upward load instead of a downward load, then it would be the opposite. So basically, as long as the truss is in positive bending, then the top chord will be in compression, the bottom chord in tension. But here, when I say there's no redundancy, what happens if I remove a single member from this truss? Just one member. The whole thing is coming down. If I remove just one member from this truss, the entire thing is going to come down, every single bit of it. So in a large building, in a building with a large frame or something like that, typically if one column comes out, you might get a local collapse of some sort. You can. There are cases where you may. But there are many cases if one column falls out, if the column spacing is close enough, you might, if one column gets knocked out or it needs to be removed for construction or something like that, or it needs to be torn out and replaced or something like that. There are cases, now I guess a cautious contractor would put up temporary shoring of some sort, I hope, if they were wise, but typically in certain buildings, depending on the forces involved, if you remove a column, you may actually be able to get away with temporarily distributing load to other columns without causing catastrophic collapse. So that is one of the major advantages of indeterminate systems. But anyway, next I'd like to define stability. Stability, fundamentally, represents this question. When we ask whether something is stable, we are saying, is a frame capable of resisting load in all directions? Some level of load in any direction. It doesn't have to be a large amount of load. It can be a relatively modest amount of load. So, but as long as it has some decent capacity representing some portion of its overall strength, we would call it stable. So, for example, or in other words, it must be able to resist vertical forces such as self-weight, lateral forces like wind, and moment. So just because something is not actively falling over under the loads that are currently applied, or I can say stability is a property of geometry rather than applied loads. Geometry alone, rather than applied loads. Let me give you a very simple example. Let's look at the flagpole condition, or better yet, imagine something even more, actually flagpoles cantilever should be fairly stable, but imagine a frame like this, a very simple frame, a one-member frame. Imagine I have a frame like this. I have a pin joint, and there's a column on top of it. And then let me show you the loads that are applied to this. Let's say there's just one single load, a downward 10 kip load. With the loads that are currently applied to that structure, is it going to immediately topple over? No. In an idealized case, assuming we need like a ridiculously idealized case, but then again, I suppose the pin connection is idealized in the first place, but it would actually have some moment capacity most likely in the real world. But anyway, as I've drawn this, this would not immediately topple over. There is a 10 kip load. There's no horizontal load. The vertical load, as long as this is not like as long as this load is nice and lined up, it's going right through the centroid of the member. As long as the pin support is along the centroid of the member, as long as everything's nice and plumb and true, and the member is straight and there's no curvature to the member or anything like that. If everything's perfect, this is not going to topple over. This is basically a pencil hanging or standing up on its eraser point, or standing up on its end point even. And so while this is not immediately toppling over, is this stable? No, it's not stable, because this system, it can resist vertical force. This frame can resist vertical force. And it can resist lateral force. Well, after it falls over anyway. But it cannot resist any kind of moment. So the moment that a slight breeze comes along, this thing is going to topple over. It is fundamentally unstable. So what this comes back to is, again, stability is a property of geometry. I don't care what loads are applied to this. Stability equals geometry. We judge whether a frame is stable regardless of what loads are applied to it. And a few caveats as well here. To be stable, the frame must resist not only motion, but changes in internal geometry. One, motion, and two, changes in geometry. Changes in geometry. So for example, imagine I draw or I build a really, really poorly designed truss. I don't know why you would do such a thing, but let's say you did. Here, let's say I built a truss like this. Or, yeah, that would work. And then let's say I have it like this here. I'm going to put a pin right there. Going to have more truss over here. This is an extremely poorly designed truss. You would definitely lose your license for building something like this. Don't do this, please. Or if you do, I didn't teach you structural analysis. And let's say there's plenty of ground for this thing to roll along here. Okay, anyway. So I've taken out the top chord and built this and put a ridiculous, well, I guess it would still have a pin regardless of whether it was I drew it or not. We usually assume pins for trusses. I guess that would be the one caveat for the previous case I told you where we assume frames have fixed joints. If it's a truss, it's a truss. But let's think about this. Is this truss, do I have to worry about this truss going anywhere? Well, I mean, sorry, really like moving or really like, is anyone going to be able to take this thing away? Is anyone going to be able to hitch a truck to this thing, tow it away, and sell it by the pound? No, it is fixed to the ground, or it is immobilized. But the geometry is not stable. The moment I apply any load, or actually even the self-weight of this thing's just going to flop down and basically fall into the river here, or whatever is here. And in fact, even if I made this a pin support, the same problem would exist. And this becomes very apparent when I look at the pin support case. So even if this is a pin support as well, now this truss is completely stationary. It's not going to move left or right or anything else, but it's not going to have any bending moment capacity. It'll have no bending moment capacity. So basically these members will just end up going into tension, and this thing will just flop down and end up going something like this. Without that top chord, this truss is just going to fall into the river as well. It completely loses any capacity. So again, though, it all comes back to geometry. This is not a case of, in this case, a truss like this, it is capable of resisting global motion of the frame, but it is not capable of resisting, changes to internal geometry. And we could have the opposite. Like I could have a, can anyone give me an example of a frame that is resistant to changes in internal geometry, but not resistant to changes in motion?
Like scaffolding?
Scaffolding would be a great example. Or, even just a simple car. We don't usually think of cars as frames, but in a way they are. And yeah, I mean, they have enough strength to resist changes in internal geometry unless you get in an accident or something, you ram your car into a wall, the frame will not resist changes to internal geometry, hopefully. I wouldn't want to be in a car that would. Yeah. So, but of course, a car would be pretty useless if it did resist motion. So, anyway. Okay, so I want to look at how to actually calculate determinacy. So, determinacy here, or determining determinacy. So now that I have defined them to death, first, I want to define a variable n that we will see. N is the number of pieces a frame is divided into for analysis. Yes, that's a poorly drawn pound sign, yes. The number of pieces a frame is divided into for analysis. A few notes here. N need not be equal to the number of members. Can be greater or less. So for example, if I want to solve for the shear and bending moment at a point within a beam, well, then I'm actually cutting using the method of sections somewhere along the beam. So I'm dividing a beam into multiple pieces. So you can end up with n greater than that. Or you can actually divide something. You can divide your pieces of analysis don't necessarily need to be the same. Don't need to necessarily be the number of members, etc. So let me give you a few examples. Let's say I have a frame here. Everything connected in fixed joints, and I just analyze this as one big rigid body. In this case, n would be equal to 1. If I just analyzed everything as one big rigid body, just a single frame here, this would be n is equal to 1. Let's say I cut a piece of this off. Let's say I cut the right column and a portion of the right beam out. So I cut it there. Here, what would n equal?
2.
Yeah, 2. In that poorly drawn column. So here, n would equal 2. What if I made a cut plane across here? I basically cut out the top beam. So let's see this. I would have this here, here, here. And then the bottom half of the column, or the bottom portion of the columns here. Well, what would n equal? Yes, very good. N equals 4 in this case. And then I could keep going. Let's say I separate it out like this, 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 n would equal, got my supports here. What would n equal? Yes, very simple, n would equal 5. And if I wanted to really go nuts, I could divide each column into two, divide each column and beam into 2 pieces, and divide everything up in an exploded view. And I would just have fun all day long, and n is equal to 10. In this case, n would be equal to 10. So that's n. That's our first number we need to define. Next, I want to define r. And r is going to be a little bit simpler. But I do need to give a few notes on this as well, because it's a little bit more complex in structural analysis than we deal with in simple statics. So r is going to be equal to the number of reactions. And this includes 2 things. A, the actual proper external reactions. And B, the internal forces revealed at a cut. So for example, if I have a beam here, let's say I have a simply supported beam. Now, as this is drawn, as I'm analyzing it as one big object here, I would have a reaction here in the vertical, a reaction here in the horizontal, and a reaction here. And R would just be equal to 3. However, what happens if I cut this thing somewhere in the middle of the beam? If I do that, now I'll now have 2 objects, and I would have internal forces. So let me show all of the forces here. Yes, well, let's see. Let's see what happens. You said 6, but is it really 6? But I see 9 arrows though. Can't you count? I mean, come on, you got to your junior year of college and you can't even count? 1, 2, 3, 4, 5, 6, 7, 8, 9. How hard can this be? Obviously, it's 9, right? Huh? Oh.
I was gonna say, just go back to Sesame Street really.
Yeah, just go back to Sesame Street. Yeah. No, sorry for insulting you. No. You are right. I am wrong. This is, of course, r equals 6. Because this would be something like, I don't know, you'd have maybe a by, that sort of thing. Bx, mb. Though I do draw 6 arrows, this, of course, only 3 internal forces. So they're the same forces, just at 2 different objects, equal and opposite, that sort of thing. So that is something that always ends up tripping people. That is something that always ends up tripping some people up on the exam, so please be aware of that. Okay, let's see here. Next, let's look at how we actually mathematically determine whether something is statically determinate. So statically determinate, static determinacy. So let's see here. Again, internal forces, well, I already defined this, but to determine whether something mathematically is statically determinate, and usually this is better than trying to just eyeball it, the equation is going to be something like this. Well, actually exactly like this, not something like this. If r is equal to 3n, it is statically determinate. If r is greater than 3n, it's going to be statically indeterminate. Will be statically indeterminate. So in other words, if the number of reactions is equal to 3 times the number of objects, or the number of members, or actually, again, n is the number of objects that you're analyzing, that you're breaking the frame or whatever into here. But anyway, now, things that are indeterminate are classified according to degree of indeterminacy. Structures are classified by degree of indeterminacy. Are classified by the degree of indeterminacy. And this will be important for later techniques. We'll need to know this. Some of the more advanced techniques we learn later in the semester. And the degree of indeterminacy, maybe I'll do this in red. The degree of indeterminacy is equal to r minus 3n. So we'll say something is, the way we'll state this is, for example, a frame is indeterminate to the 2nd degree or something like that. Or indeterminate to the 1st degree, that kind of thing. To the 1st degree or 2nd degree. So we have 1st degree determinacy, 2nd degree, 3rd degree, etc., etc. Okay, some other notes on degrees of determinacy. I think I'll just finish up with this. So one thing to keep in mind here are, let's see, yeah. important. The degree of indeterminacy is independent of the number of objects you break your frame into. Let me show you by example. So let's say I have a simply supported frame here. And then let's see. Oh, also, no, it's broken into. And also, I can give another note here. There is one important exception to this. If a member, or any frame, I should say, any frame that has a closed loop of members must be broken up. Must be broken up, and a closed loop of fixed members. Basically, members must be cut to break the loop. And I'll draw out what this means. Otherwise, the incorrect degree of determinacy will be reached, will be calculated. Incorrect degree of determinacy will be calculated. Degree of determinacy will be calculated. Will be calculated. And I just want to finish up with a couple examples. Looking at how we can calculate whether something is statically determinate, indeterminate, degree of determinacy, etc. So I want to illustrate this, these two things via some basic examples. I want to illustrate this with some basic examples. Okay, so what I want to demonstrate is I want to just demonstrate two things. One, I wanted to demonstrate that the number of sections you break something into will not affect the degree of indeterminacy, and also that and the one exception to that is a closed loop. So example here. Let's say I have a simply supported frame. And then let's see what happens when I break it up into a different section here. Something like this, and then one here. Like that, and like that. So if I show the forces here, the reactions and reactions, I would have the same reactions here. But then when I cut it, I would have internal forces as well. And I'll just draw the top ones for expediency. Well, maybe I'll just go ahead and complete it. To the left, down, to the left, down, and clockwise and clockwise. In this case, n is equal to 1, and r is equal to 3. So r is equal to 3n. And so it in fact, is determinate. Confirmed. It is not statically indeterminate. It is statically determinate, so that is perfect, nice and statically determinate. Then, what about in this case? Well, n is equal to 3. I divided this into 3 pieces, and r now, though, is equal to 9. So r is still equal to 3n, and still determinate. So yes, we divided the thing up, so still determinate. So yes, we divided the thing up, and that gave us more internal forces that we had to worry about, but it also gave us more members that we could solve for equilibrium about. So we did not change the determinacy based upon that. Okay, so then I'll let me show another example, something a little more complex. Let's say I have a frame. Actually, I'll draw this on the next slide. I'm going to show a slightly more complex frame, and this will be indeterminate to actually a very high degree. Consider a frame like this. And let's say I did something like this. Oh, let's have a little fun. I'll have a taller section in the middle, though it won't really matter. Maybe fixed, and then for whatever reason, off to the sides, I have a couple columns attached to this with a pin support, with pin supports. Like this, and like this. And so then the support reactions here, like this, all three here for the fixed support, all three here for the fixed support, and just 2 on here. So in this case, n is equal to 1. I'm analyzing this entire frame as a single rigid body, so n will be equal to 1. R, however, if we count, is going to be equal to 10. So we know that R is not going to be equal to 3n, but R minus 3n, 10 minus 3 times 1 is 7. So this is indeterminate to the 7th degree. This is indeterminate to the 7th degree. Now, what happens if I break this frame into pieces? Let's see if I might think, oh, what if I just divide this thing up? Can I get a different result by breaking into pieces? Maybe that'll help me somehow. You probably know the answer already. You can probably just get there by using the conjecture there's no such thing as a free lunch. But that's okay. Let's just illustrate it properly, or illustrate it fully. So let's say I divide this into pieces like this. Here. And then like this. Then I'll show the forces on this. There's going to be a whole lot of forces. The 3 here. So again, 2 here and 3 on each of the middle ones. Like this, and then we would have this, you know the drill by now. Assume whatever direction you like, as long as they're equal and opposite. Here, 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 and here, here, and here. Now in terms of reactions, I'll have 3 here, 3 here, 3 here, 2, 3, 3, and 2. So this gives me, well, first of all, I'm going to have an n equal to 4. My n is going to be equal to 4. That's the number of pieces I've broken this into. And if I counted properly, I get that r is equal to 19. And what do you know? R minus 3n is going to be 19 minus 4 times 3, which again will be equal to 7. So again, it is indeterminate to the 7th degree. So I can divide this thing up into as many pieces as I want, but no matter what I do, it's still going to produce the same levels of indeterminacy. There is, however, one exception that I really want to illustrate in this as an example, and then we'll be done for class today. To 7th degree. And then and what I want to illustrate is the closed loop example. Okay, now let's consider the closed loop example. So again, determinacy is always the same regardless of the number of steps or the number of sections. The one exception is closed loops. Is closed loop. So imagine you have something like this. Now, I don't know why you would build a frame like this. It's a kind of a goofy looking frame, but it does illustrate the idea fairly simply. So let's say we have a two fixed columns, and I'll go with the simplest kind of closed loop you could have. That would be a triangular loop. Well, assuming you had assuming you had straight members, the simplest kind of closed loop you can get is a triangle, although most closed loops you get are going to be rectangular. Let's see, let's look at the reactions in this one. Here, I would have 1, 2, 3, 4, 5, and 6. So if I analyze this as one piece, I would say, oh, n equals 1 and r equals 6. So this, I would report that this is indeterminate to the third degree, r minus 3n. Instead, let's see what happens when we cut this. Let's say we cut this, and we look what kind of forces are revealed, and we redo our calculation of r minus 3n. So I'm going to cut this thing right here, basically. Cut it right there and right there. So I'm going to have two pieces now. I have this piece here and this piece here. And then this will go up like this, and then back down, and then this, and this. And then my internal forces, the reactions are still, the bottom reactions, the support reactions are still going to be the same. But now I'll have revealed an additional 6 internal forces. So boom, boom, down, up, clockwise, counterclockwise, or opposite actually. Here. You know what, actually I'll go show this. Maybe I can show this global X, global Y. Oops, I erased one of my members. That's not good. Shouldn't erase members. So I can show X and Y forces on this one here. Something like this, and a moment, this, and an opposite moment. And in this case, my N would be equal to 2, but my R would be equal to 12. And R minus 3N would be equal to 12 minus 3 times 2, and it would be equal to 6. This frame is actually indeterminate to the 6th degree. So the moral of this story is, the moral of this lesson is, or not the lesson, but at least this example here, we got the incorrect result when we did not break up the closed curve or the closed loop. So again, what we have to do is break up closed loops when determining determinacy. So we must break up closed loops. All right, any questions on this? And I still need to cover stability, but I think I'll cover that in a follow-up lecture. Okay. So any questions on this? All right, that'll do it for this portion of the lecture. Thank you for attending. Thank you for watching. And as always, thank you.